Hello everyone, and welcome to today's chem lesson. Today we are going to continue our discussion on balancing chemical equations with the follow-up next step. What do we use those balanced equations for? And what information is contained in a balanced equation? So let's look. Here we have a balanced equation up here on the top in bold. We have 2H2 plus O2 makes 2H2O. Now this balanced equation gives us different pieces of information at different scales. At the molecular scale, it tells us how many molecules of each reactant on the left and each product on the right are used/created. Right, we know that 2H2 can be read as 2 molecules of H2. And 1O2 can be read as 1 molecule of O2 to make 2 molecules of water. Right, we can see that visually here, right? 2 H2s is 4 H atoms. 2 O's is 1 O molecule. And here we have the 2 O's and the 4 H's come together in a different pattern, right? Taken apart and put back together as if they were Legos. The other piece of information we get at the molecular scale is the mass of these things in AMU. Right? We know that 2H2 molecules weighs 4 AMU. We know that 1O2 molecule weighs 32 AMU. And we know that 2H2O molecules weighs 36 AMU. Something to note here, this reads just like any other math problem, right? 4 plus 32 equals 36. The sum of the mass of the left will be equal to the sum of the mass on the right. Because these pieces, right, 4 whites and 2 reds, are the same thing here, 4 whites and 2 reds. Right. Now, an important question brought up here by Arthur, right? Why aren't they equal signs, right? Why don't we put an equal sign here? We don't put an equal sign here for 2 different reasons. One, let's just talk about math for a second, right? 2 plus 2 equals 4, and 4 equals 2 plus 2. Right? Equal signs are reversible, right? I can flip the contents and still have a mathematically valid equation. That's not true of chemical equations, right? This arrow is not an equal sign. It is a shortening of the phrase that says in the right conditions. Right? In the right conditions, 2H2 and 1O2 can make 2 water. There is a different set of conditions to go 2 water to break down into 2H2 and 2O2. Right? It would be the same as if saying, right, let's take it into the real world, say that 2 eggs plus milk plus flour equals a cake, and then saying you can use the same exact process to turn a cake into 2 eggs, milk, and flour. Right? Equal signs are reversible, but chemical equations are not always reversible. Right? You can't unbake a cake. There are some reactions that you can't undo. So we don't have an equal sign. We have a one-way arrow. Right, going back to our balanced equation here, we also have some information at the mole level. Right, this 2 in front of the H2, the 1 implied in front of the O2, and the 2 in front of the H2O, we can talk about them as molecules, but we could also talk about them as moles. Right, scaled up to, a factor that we can interact with, right? We can't interact with singular molecules, but we can interact with moles of molecules. And along with scaling it up to moles, we can scale up our mass from AMU to grams. Right, 2 moles of H2 weighs 4 grams. 1 mole of O2 weighs 32 grams. 2 moles of H2O weighs 36 grams. Right, all coming from our balanced equation. Right, coming from a balanced equation and the numbers found on the periodic table. Now, we're going to look at balanced equations and some questions that ask us to investigate certain things, right? For example, if I want to make 8 moles of water, how many moles of oxygen do I need? Right, if I took this and I scaled it up and I multiplied it by 4, I need to do the same thing to the whole equation, right? I need to scale things up or scale things down, right? If I want to make 1 mole of water, how many moles of oxygen do I need? Right here in this case, I scaled it down, I cut it in half, so I should cut everything in half. The same way you mess with a recipe in real life to scale things up or scale things down, you're going to do the same thing, and we're going to see the same thing with chemical equations. There are 3 calculations that we are going to focus on. We are going to look at converting from moles to moles using a balanced equation, from moles to mass using a balanced equation, and from mass to moles using a balanced equation. There is also the option to talk about going from mass to mass, but really, that's just a combination of the last 2. Right, and if you can do these individually, you can do the last one as well. Right, so we're really only going to focus on the first 3. We're going to look at them from easy to hard, right? So we're going to start at the top and work our way down. Right, easiest first and hardest last. The first thing we're going to look at, like I just said here, is mole-to-mole calculations. Mole-to-mole calculations follow 2 steps. First, we balance our equation, and second, we convert using the mole ratio. I'm going to show us how to do that in a second, but first, our first step is always to look at this question. Our first step is always to look at the equation that is given and balance it. Right, I'm going to use red from this point onwards to look at balanced equations. Right, this is the same equation we just saw in our example slide, so we know it gets balanced with a 2, a 1, and a 2. Right, that is our balanced equation. Now the second step asks us to look at our question and use a mole ratio to answer it. And what we're going to do with the mole ratio is we're actually going to set up fractions. We're going to look at proportions. And the nice thing is, if you look carefully, you can see that our numerators are already here. Our numerators are already set up. 2 over something, 1 over something, 2 over something. We need to fill in the denominator. Right here they say 1 mole of O2. So I'm going to take 1 mole of O2 and put it as my denominator. How many moles of H2O? And now I have my mole ratio set up. I know that 1 over 1 equals 2 over X. 1 over 1 equals 2 over 2 moles of water. If this equation was a little bit different, right, or if this question was a little bit different, if I had asked for If we react 3 moles of water, or sorry, 3 moles of oxygen with unlimited hydrogen gas, how many moles of water do we get? We're just going to change our denominator, right? The thing from the question should be the denominator at all times. 1 over 3 equals 2 over 6. And so 6 would be our answer. This is exactly the same concept you use when you mess with a recipe, if you scale it up or you scale it down. You're looking at the instructions, which is our balanced equation, and you're making it match what you need it to be. Right? I need 6 people to each have a mole of water, and so I need 3 moles of oxygen for that. Let's see this in action. I'm still going to keep red as my balancing equation and blue as my mole ratio. Keep in mind it's called a mole ratio. It's going to come back in a second. So here we have 3 different questions, each with an equation that needs to be balanced. So I'm going to write them out, and you can take a second if you'd like and pause here to try to balance them out yourselves. But if you are not wanting to do that, or if you're already comfortable with how you balance equations, you can just hold on 1 second and I'll jump right into answering these. Right, and here we have an A and a B. Right, so switching to red, let's balance an equation. Right, let's look at question 1. Let's make sure we write the correct formula down before we do anything else. And then let's look at balancing an equation. Right here, if you remember from our previous video, this is the formula I showed you, the equation I showed you that starts off pre-balanced, right? It's a thing that happens, doesn't necessarily happen often, but it is a possibility. Right, so 1 carbon and 1 oxygen makes 1 CO2. If I switch over to my light blue here, how many moles of carbon? So that's going to be my mystery number, right? Moles means I can use it in my mole ratio, are needed to make 4 moles of CO2. Again, moles can be plugged into my mole ratio. So now I know 1 over x equals 1 over 4. 1 over 4 equals 1 over 4. So my answer here is going to be 4 moles of carbon. Looking at my second one, I still have an equation that needs balancing here. So I'm going to start by putting a 1 in front of the biggest substance, right? There's 11 different atoms in C3H8, so that's a good place to start. That gives me 3 carbons and 8 hydrogens, which means I'm going to need a 3 and a 4 here to get 3 carbons and 8 hydrogens. That gives me 6 oxygens and another 4 oxygens, so I get 10 oxygens on the right, which means I need a 5 here to get 10 oxygens on the left. Equation properly balanced. I switch my color here. How many moles of O2, right? Again, moles, keyword, means that I can put my question mark under here, will react completely with 5 moles of C3H8. So now I have my proportion set up already, right? 1 over 5 equals 5 over x. 1 over 5 equals 5 over 25 moles of oxygen. moving on to our third question here, we've got an equation that needs balancing. We can start with a 1 in front of our biggest thing. All right, that gives me 1K, 1Cl, and 3 O's. A 1 here works well, right? 1K and 1Cl. But I have to get 3 O's. 1 O2 gives me 2 O's. 2 O2s gives me 4 O's. So I skip right over 3. So a 1 doesn't work in that spot. What about a 2? That means a 2 is going to go here. I've got 6 oxygens, and I can get 6 O's with a 3. For question A, if we start with 2 moles of the reactant, right, that brings in a vocab word, right? Reactant is the thing on the left side of the arrow. So if I start with 2 moles of the reactant, how many moles of each product will I make? Right, product is the thing on the right side of the arrow. 2 over 2 equals 2 over 2 and 3 over 3. So we're going to say 2 KCl and 3 O2. For B, if we start with 1 mole of the reactant, how many moles of each product will we make? In this case, we're going 2 over 1, so we're cutting things in half. 2 over 1 equals 2 over 1. And 3 over 1.5. It's okay to have a fractional or decimal answer, but remember, it is not okay to have anything other than a whole number when balancing the equation. Right, so summarizing here, you're balancing your equation every time. You're making sure that they are talking about moles, because when we're using our mole ratio, when we're putting things in the denominator, they must be moles. And then you're going to get answers out that are moles. When we go to check our answers, we're going to see 4, 25, 2, 3, 1 and 1.5, 4, 25, 2, 3, 1 and 1.5. When we look at our second type of calculation here, we're looking at mole to mass, which is going to be the same 2 steps as before, with 1 extra third step added in. And that third step is going to be converting our unknown moles to grams, right? Looking at the periodic table, to calculate gram formula mass. Right. So, how is that different, Mr. M? Let's look at an example. We have our equation that must be balanced. All right, so stick with my red. We're going to balance our equation. The same equation we looked at before. I'm going to switch over to blue to use my mole ratio. I have 3 moles of O2. How many grams of water will be produced? Right, 3 moles of oxygen. Good. How many grams of water? Now, this question mark isn't going to give me grams of water. This question mark is going to give me moles of water. 1 over 3 equals 2 over x. 1 over 3 equals 2 over 6 moles of water. Right? That's not my answer, though. I have moles. I want grams. And so that's where this third step comes in. I'm going to have to check my periodic table and calculate H plus O 1 plus 1 plus 16. 18 grams is 1 mole. So then 6 moles, and I have another proportion set up for me. And when I solve this proportion out, I am going to get my final answer, which is going to be 108 grams of water. All right, again, 18 over x equals 1 over 6. 18 over 108 equals 1 over 6. And that is my final answer. So the same 2 steps as before, but instead of ending with moles, they're not asking you for moles. They want grams. So you got to do this extra step, this extra calculation to solve that out. Let's see this one in action. Right here we've got 3 different parts. And so we're going to break this down into 3 different sections. We have one equation that we're going to use for all 3 of these. So when we balance this out, right, we're going to recognize that it's the same one that we were looking at before. So we've balanced our equation. That's our first step. Then we're going to look at our problem. We're going to see how many grams of CO2 will be produced when 1 mole of C3H8 reacts completely. And so we're going to pull our necessary pieces from our equation. We're going to look at what we are given here, right? We're given 1 mole, and we're asked about carbon dioxide. 1 over 1 equals 3 over x. 1 over 1 equals 3 over 3 moles of CO2. I can't stop there. They asked me for grams, so I must go to my periodic table and find some values. Right? C plus O plus O, 12 plus 16 plus 16. That's 44 grams equals 1 mole. So 3 moles equals how many grams? Again, we have a proportion set up for us. 44 over x equals 1 over 3. 132 grams of carbon dioxide is going to end up with our, or as our, final answer. For the second one, how many grams of H2O are produced when 5 moles of C3H8 reacts completely? So again, we're going to pull our necessary pieces from our balanced equation. All right, we know a 1 and a 4 go here. How many grams of H2O? 5 moles of C3H8. 1 over 5 equals 4 over x. 1 over 5 equals 4 over 20 moles of water. But they don't ask me for moles, they ask me for grams. So I've got to do one more set of calculations here. H plus O. 1 plus 1 plus 16. 18 grams is 1 mole. So 20 moles is going to equal some other number. And again, we have our proportion. 18 over x equals 1 over 20. 18 over 360 grams of water equals 1 over 20. And that is going to be our answer. Right? These proportions are made for you as you set up the problem. Let's look at our third one. How many grams of carbon dioxide will be produced when 0.5 moles of C3H8 reacts completely? So again, we're pulling out carbon dioxide and C3H8, taking our numbers from our balanced equation. We have grams of CO2, 0.5 moles. So moles is going to go in the bottom. We're going to put that question mark there. 1 over 0.5 equals 3 over x. 1 over 0.5 equals 3 over 1.5 moles of CO2. They ask for grams, so I need to go back and do my calculation, right? C plus O plus O, 12 plus 16 plus 16, 44 grams is 1 mole, so 1.5 moles is question mark, right? 1 over 1.5 equals 44 over 66 grams of carbon dioxide. Another little trick that we have here, right? If we look at our answer for A was the exact same question, but instead of 0.5 moles, it was 1 mole. So if we look at the relationship between A and C, A should be double whatever our answer for C is. If we take 66 and we double it, we do get 132. Right? There are always multiple different ways to approach these kinds of problems. I'm showing you what I believe to be the most efficient way. When we go and we check our answers, we should see 132, 360, and 66. So let's check them. 132, 360, and 66. And that's going to lead us to our final type of calculation, mass to mole calculations. And here we're going to see the same 3 steps. We're going to balance our equation. We're going to use our mole ratio. And we're going to do some arithmetic. Except instead here, we're doing them in a little bit of a different order than we just did. Right? Instead of doing our periodic table calculation at the end, we're going to do it before we use our mole ratio. Right, but it is still the same 3 steps. So we're going to start by looking at our equation and making sure it is balanced. Right, we know that this balances out with a 2, a 1, and a 2. And then we're going to look at our equation, or our question. Right, they give us 48 grams of oxygen. Now, the thing you want to avoid is this. You cannot put grams in your denominator here. Right, this is only for the mole ratio. They must be moles if you're going to put them down here. So I need to say 48 and convert that to moles. So I check and I say O plus O, 16 plus 16, 32 grams equals 1 mole. So 48 grams equals something. 32 over 48 equals 1 over x. 32 over 48 equals 1 over 1.5 moles of oxygen. Moles, I have a value that I can stick into my denominator. And I'm looking for moles of water. 1 over 1.5 equals 2 over x. 1 over 1.5 equals 2 over 3 moles of water. And that will be my answer here. Right, just like before, let's see these in action. Here you have 2 questions that will come with formulas. You will not have to write formulas out for yourselves. We're going to look at our steps here, right? First step is always going to be balancing our equation. Right here we look 1 sodium on the left, 1 sodium on the right. 2 chlorines on the left, 1 chlorine on the right. We got to fix that. So we put 2. Right? 2 chlorines, 2 chlorines, 2 sodiums, 2 sodiums. Equation balanced. Right? Then we go and we take a look at our equation, or our question. 100 grams of chlorine gas. Right? If we're going to do anything, we need to find out what chlorine weighs. 35.5 plus 35.5 gives us 71 grams is 1 mole. So 100 grams is something. 71 over 100 equals 1 over x. 71 over 100 equals 1 over 1.4 moles of chlorine gas. Now that we have moles, we can plug that number into our mole ratio. Right, they're asking us for moles of sodium chloride. So 1 over 1.4 equals 2 over x. 1 over 1.4 equals 2 over 2.8 moles of NaCl. And that is going to be our answer here. In our second one, we have another equation that needs balancing. We need to put a 2 in front of the aluminum oxide here because of our odd number of oxygens. Right? So if you tried putting a 1 there, you'd find that it doesn't work. A 2 gives me 4 aluminums, 6 oxygens. 4 aluminums, 6 oxygens. Then we look at our question. What do they give us? 300 grams of aluminum. Remember, that's a big no-no. You cannot do that. Grams cannot go in your denominator. We must save that spot for moles. So we need to convert this into moles. Aluminum, we can look at the periodic table and find out that 27 grams equals 1 mole. So 300 grams equals something. 27 over 300 equals 1 over x. 27 over 300 equals 1 over 11.1 moles of aluminum. Now that we have moles, we can put that in our mole ratio. They're asking us about moles of aluminum oxide. 4 over 11.1 equals 2 over x. 4 over 11.1 equals 2 over 5.55 moles of aluminum oxide. And that will be our answer. So here we end up with the same steps, just in a slightly different order. Right? You must have a balanced equation. You must use moles as your denominators. So if they give you mass, you need to convert it to moles. If they ask for mass, like they did before, you have to take your moles and convert it to grams. Your proportions are made for you if you keep things lined up, right? Grams over grams, moles over moles, grams over grams, moles over moles. And as long as you keep your numbers straight and you line up your things, right? My mystery thing here is aluminum oxide, so my question mark goes under aluminum oxide. If you do these carefully, everything is set up for you. With that, I am going to transition us over to our Google Meet for questions, comments, concerns, and attendance. And I will see you there.